Okay, I can start. We have to make sure we're recording. So, good morning and thank you for joining us for our CGD seminar this week. I have the pleasure of introducing Andy Wood as our speaker this week. And today, Andy will speak on, the title's the same, Advances in Land Surface Modeling and Prediction to Support Risk-Based Water and Emergency Management and Planning. For those of you who don't know Andy, he's a project scientist in CGD and a research professor in the Department of Civil and Environmental Engineering at Colorado School of Mines. Just prior to moving at NCAR, Andy was a development and operations hydrologist in NOAA NWS Forecast Center in Salt Lake City and Portland. I don't want you to have to look at his CV. It's many pages, so I'm summarizing it. What I found interesting is Andy has a Bachelor and Master of Arts in English from Amherst College, and then a Master of Science in Engineering and a PhD from the University of Washington. He's nationally and internationally recognized in advancing the science and application of weather and climate information for hydrology and water resources, with a particular focus on monitoring, prediction, and climate change impact. Most recently, he's expanded his focus to improve the land surface component in coupled models, in particular in the community Earth system model. And he's also co-lead of the NCAR Extremes Affinity Group. So as in past seminars, we'll take questions from those of you in person, but this is also being broadcast on YouTube. So at the end of the talk, we'll also have questions from that. If you're, just a reminder, those of you that are joining us remotely, use the Slido link to input your questions. And you can find the link on the YouTube page or by going to slido.com and looking up the CGD seminar. So Andy, take it over.
It's nice to have this opportunity to talk about some of my background. It's not a super long talk, even though it seems like an hour is a long time to weave in a lot of different things. So I've tried to kind of construct a narrative out of disparate elements. And if it leads me to do any sort of gross mischaracterizations of the science or other people's work, I apologize for that in advance. So this is going to be about actionable science. It's particularly in the land modeling area in support of stakeholders, and it is motivated in some part by all the discussion that we hear today at NCAR and in the community about convergent science, co-development, actionable science, trying to connect Earth system science to decision-making stakeholder needs. So the talk has three parts. There'll be a bit of a background looking back, not quite so far back as my English major time. I'm sure people don't want to hear about Russian literature and modern American poetry. And I don't even really remember a lot of that stuff. But it will go back to the beginning of my sort of career in the climate change or science world. So anyway, and that goes back to about 1999. Previous to that, I had started a master's, and I did a bunch of work as a sort of systems engineering water resources specialist on building models to assess the impacts of climate change on US water resources systems. And I wrote this paper while I was working at the policy office in the Corps of Engineers back in Washington, D.C., which was a very interesting experience. I got to interact with people in Congress and the head of the Corps of Engineers and the Pentagon and whole host of characters. But what we were doing was civil engineering, essentially, projecting out these implications on these big basins. And there's some interesting things about the work at that time, aside from the fact that it was apparently back in the black and white days of papers, either that or we were too cheap to pay for color. But in any case, we do these studies and we would really try to go from end to end. So starting with GCM-based climate projections, all the way down to system models and metrics of impacts on all kinds of different sectoral. Let's see if I could get a pointer to work here. All these, I guess it's going to come out as a arrow, but all these different sectoral concerns that these water resources systems are run for. So this is the Missouri River Basin or river system, and it has a lot of objectives that it's used for. And so there's sort of already a chain of modeling starting to form up back in this particular day. So we published that study, and then flash forward, I went back to the University of Washington to do a PhD, but this time I felt like a lot of the problems are actually solvable more in the hydrology Earth system world than in the water management world. Water management is a big part of it, but if we don't understand what's going on with the climate and the hydrology from more Earth system perspective, we're not going to fix it with the water management. So anyway, there I led a number of papers and developed some new sort of techniques in the field. One of the key papers was this one where we compared using dynamical and statistical downscaling methods for climate to provide inputs to hydrology models, along with colleagues like Ruby Leung, who's at DOE PNNL. And one of the sort of takeaways from this was that neither GCMs or RCMs are really, applied to downscale GCMs are really adequate for providing inputs to land models. And so that was kind of a pushback against people sort of saying, oh, now that we have models like WRF, we can just downscale the global climate and we'll get good impact assessment information. This also sort of introduced this idea of quantile mapping and CDF matching. It's now been around a really long time, but this was something that I found I had to apply because I was myself discovering that you could not just take outputs from global or regional models and put them into hydrology models. They were too biased. And back then we're working with a really old model, the global spectral model. And then this became part of a technique called BCSD. This paper has been cited over 2,000 times. It's got used for many, the technique got used for many application studies. And just to comment on what I was seeing kind of as a first-year PhD student was pulling model data for regional climate out of the global spectral model AMIP runs and realizing it had sort of massive biases even in temperature, which we think of as a little better than precip as well as precip. So I basically came up with this idea of doing this probability matching technique to do the correction. It was something I'd done for streamflow before to try to correct for model low flow biases that I couldn't get out of the land modeling, but it sort of found its way into a whole bunch of different papers and then various techniques. And actually at the time, it was a little controversial because climate modeling groups would feel that it was somehow too engineering minded for what they were trying to do. And I actually got some screeds from climate modelers saying, hey, look at this. This is ridiculous. You're breaking the mass energy constraints, and we could take this and make North America look like South America if we want to, and this really isn't the way to go. And now, of course, this kind of thing is done everywhere. So we moved on with this kind of ability to do a whole bunch of regional studies, still black and white days, but in basins around the Western US, looking at effects of climate change on hydrology and water resources. This is just an example of now using sort of transient runs from the climate models and coming up with, unfortunately, this was just one old climate model, PCM. I don't know if any of you remember that particular model from DOE. I think it had a very low climate sensitivity, but it was still, it's more about developing this communication with the stakeholder communities. And notably, a lot of this work was funded by stakeholder communities. And so as we start to realize that we can do this kind of modeling for the climate change, we also start looking at problems like shorter range prediction. And one of the notable things about shorter range prediction is it's done operationally with very low dimensional, low complexity conceptual type models. So the Sacramento model's been around for 40 years. And what tends to happen when you have this kind of model is that you can do parameter tuning and find sensitive parameters and then optimize them so that you actually get a good simulation at the end. And I wonder if I could restart this somehow. because it's kind of striking. Sorry, I'm just going to pause this and see if I reload this slide. So basically, you take a structure like this. We often talk about a model as if it has a certain climatology and a certain physics, and that whatever emerges from that model as a simulation of hydrology and climate is a result of the physics. But early on, when you start to look at operational hydrology with simpler models where they pay a lot of attention to parameters, you realize basically, depending on how you merge the parameters with these parameterizations, the algorithms, you can get quite different emergent behaviors. And this is something that's, of course, the first thing you do if you're not doing coupled or system modeling, and you are doing something that has a very applied objective. So you can see how well, like in the right, the kind of like monthly climatology of streamflow can be made to match observed streamflow if you go through this kind of adjustment, optimization, parameter estimation process. So at the time we thought, okay, well, major advance we can bring is we can up the complexity of the land modeling from conceptual to something more like a land surface model that you might use as a boundary condition for a coupled GCM or RCM. So the model we developed at the time, I was at University of Washington, was the VIC model, variable infiltration capacity, column model, not unlike a lot of other land models. And we figured out ways that we could do what the operational groups were doing and essentially develop sort of large scale, continental scale reanalyses, but actually do the parameter estimation and calibrate the models so that they gave good responses on a lot of at least large scale river basins. So this is an example of another paper. This has also been cited about 2,000 times, and it became a major part of a lot of development in land modeling at the time. I started plowing these kinds of models into applications. I built sort of the first modern land model-based drought monitor that I ran operationally at the University of Washington. Built the website, built all the data feeds, forcings, and interfaced it with different drought groups in the US. So this is back in the early 2000s. I used it for regional prediction. I built and ran a seasonal prediction system for about 5 years using, again, the VIC model, and the advance was kind of like going up the complexity scale from conceptual models to actual land surface models. So this is this idea of, how can we bring earth science or kind of hydrological science into this more applied approach. So we did that. And since then, I've been doing a lot of the same things. I actually took a 2-year detour after building that, worked for a private company. We made seasonal forecasts and also shorter range like solar and wind forecasts for global and regional and climate domains. We sold seasonal streamflow forecasts to banks who were doing like energy trading. It was really very upfront and hands-on with people who are kind of stakeholders, decision makers, making real decisions with real money, using some of this earth science modeling. And so now in NCAR, I've been for about 10 years interacting with different groups, reclamation, US Army Corps of Engineers, to try to answer problems that they're having in different basins, such as down in the Rio Grande, where there's this perception that things are drying out. We're kind of losing the ability to convert precipitation to runoff, which is what they need to manage the water. There's a lot of concern that we're in a new normal where, we will never get back the kind of productivity of our hydrology that we've had in the past. Another one is just how can we better manage reservoirs, like this one up north of us, Buffalo Bill near Cody, Wyoming, where we really need to be able to predict seasonal variations in inflow. So we can use some of the modeling that we're doing at NCAR to build predictions that they can then go and use to develop operating rules for these reservoirs. Another one is I've been working for a long time in Colorado, really almost 20 years, on this kind of upper Colorado climate change problem that also sort of intersects with the seasonal management problem, and the stakeholders there, which encompasses the whole Southwest, essentially really would like to see better 2-year predictions, even better 5-year predictions, and also understand what's coming. I don't know if you've been seeing headlines around the Colorado Basin, but they're kind of every day now as they face water shortages. So, we're basically really trying to get at this with better earth science modeling, better earth science uh, information from climate predictions and projections. And it's feeding also into federal and state level policy and planning. So some of the work that we've done has fed its way into these reports. And basically we're kind of like turning a well-oiled crank at this point, within the community, based on some of this work that stretches back 20 years, where we have this sort of chain of models approach, where we go through, we take, GCMs, forced by emission scenarios with different ensembles, initial conditions, downscale it, put it through a hydrology model, and hopefully we calibrate the model, although that's still, as many of you who work on this in here know, it's a challenge. And we end up with these like hugely uncertain projections. We want to be in a place where we have some way of distinguishing at each of these levels where this uncertainty is real and where we're just including bad models or bad information, and thereby reduce uncertainty. And so I think this kind of crank we've been turning has started to show its limits, especially as we go into a place where instead of a few BAUs or RCPs, now we have a ton of SSPs, we have a ton more ensembles, a ton more GCMs. There are many hydrology models. There's like 24 downscaling methods. I mean, at that point, you can just say, oh, this is all, these are all valid, so let's just add them to the pot, and then the uncertainty of the result is just unusable. So we're kind of in that phase. One of the things I've done recently with colleagues in RAL is I sort of outlined this idea that we should be starting to bring in ideas from the prediction context where we actually verify everything we do. If we're going to make seasonal predictions, we have 3 models. We verify to see which one is best or if we can combine them, if we have different downscaling methods. Obviously, that's a lot easier to do if you're looking at a seasonal prediction than a 1-century scale projection for which you have no real observations. But the idea is we need to bring in that thinking so that we can actually start to discard some of the modeling and options that are available to us to hone in on the ones that really we feel would provide more reliable long-range information. So we have this sort of 3 and now 4-part project where Andy Newman from RAL was focusing on ESM scenario selection, Ethan was focusing on downscaling, I was focusing on hydrology. And hydrology is by far the easiest part. I've been able to stand up a number of, I guess, resources for assessing hydrology and doing applied projects in the Western US. I've been using a model called SUMA, which is a Fortran-based kind of multi-parameterization model. It's actually very cleanly written. It was developed here by Martin Clark and others. And then we have various nice ways of making meteorological inputs. And we've stood up a sort of intermediate, or I've stood up sort of intermediate complexity model that I can use for all these water, these basin studies for the Reclamation, Corps of Engineers, and other groups. Here's just an example of kind of the intermediate scale model being applied to the reclamation domain only, where they manage water in these regions in the West, from which it's about 55,000 watersheds. I've tried, after decades of modeling on grids, I've tried to move to modeling on watersheds. I think it's a little easier to communicate with people in the water energy domain. And we've done studies that are small, such as just inflows to Lake Estes up in Estes Park, or working on inflow predictions for Lake Tahoe, particularly given that we have a lot of snow up there this year, to regional and national scale. I'll just show an example for the Pacific Northwest. We're using this kind of modeling. And there they have both short-range, seasonal, and climate change scale modeling questions. We're using this kind of modeling to simulate the basin at this intermediate scale, which gives you these nice sort of spatially varied depictions of things like soil moisture, snow water equivalent, river flow, and so on. And again, this is all important to establishing like the credibility of the modeling for the purposes of the stakeholder. And we can make seasonal predictions that either are very detailed at the short flood scale for flood forecasting or long-term going out a year for inflow management. This system I set up to run on Cheyenne and Casper every day. It cranks out new ensemble forecasts for the whole domain. It has a nice scheduler from ECMWF that was implemented. And I have some help on this. It's not just me alone. Colleague Josh Sturdivant's working on it. We also use the modeling for national scale assessment in the climate change arena. This is from a NASA-funded project to kind of embed our modeling into their land information system and use some of the routing and downscaling tools with that. So it's just, there's a lot. So this is a little bit of a survey of a collection of projects, the point of which is really to just show that we interact with a lot of stakeholders, and it's very applied. And even though we sit at the front, sort of the tip of this institution, NCAR, which has massive capabilities that are focused on Earth system science, there is sort of a cadre of people in NCAR who are also trying to bridge this gap to having our expertise as well as our models be useful in applications. There's another application I'm involved in, national scale, is helping build this next generation water resources modeling framework. And this is something that's superseding the WRF hydro-based NWM that was being worked on for a while in RAL. And so here the idea is actually not to pick any model. The idea is federal agencies have a lot of problems when they try to pick one model and then get too wrapped around the axle of that model and its legacy. And so the solution is try to develop a model agnostic framework so that the best ideas around different components of a land model or Earth system model could be linked in from any source and run sort of in an interoperable way. And then we can pull from any agency, any institute, any person who has an idea and put it in there. And so I was involved, for instance, in rewriting NOAA MP into something they called NOAA OWP modular, which is now connected into this framework, but it looks different from the NOAA MP. It has a different name. I think they've gone and trademarked NOAA MP just to make sure that people don't forget that that's, a distinctive thing. And then there are other models. One that's interesting is that this framework can build in not only process models, but also machine learning models, such as the LSTM at the bottom. And here's just a kind of demonstration that you could run this heterogeneous modeling solution over a whole, well, it's going to run over the whole US, but it can include a mixture of things like NOAA, OWP, as well as machine learning models, and still come out with sort of credible looking output. So this is another big project. I've also gone down to School of Mines half-time to contribute to this overall national modeling project because Mines is part of this Cooperative Institute for Research Operations in Hydrology. It's like a $360 million institute, and I was asked to lead this theme of the Institute. One of our former colleagues, Martin Clark, will be leading, or is leading, this theme. And so basically we're trying, we weren't able to do this from NCAR, but now we're trying to sort of bring and tap into the expertise we have here and bring it there through other institutions. Lastly, I'll just say, I'll check the time. I also do work on the global scale. Again, this is very different, but it's also very stakeholder driven. And the World Meteorological Organization is trying to get very heavy into the arena of hydrology and water security. And so one of the big initiatives is a global hydrological status and outlook system. It's operational. And I've been involved in that since 2017, and now lead a technical development team. And this is just kind of volunteer, although it takes real time. I had to go to Wallingford in England in January for a week to kind of manage the team and strategize about what was going to come next. But this idea is that, all around the world, we're dealing with all these kinds of challenges, whether it's infrastructure, climate change, or food and agriculture. And basically, if we can stand up a system that merges all the national capabilities with global capabilities coming out of centers like ECMWF and others that are running global, seasonal prediction models and longer, then we can kind of provide a synthesis that allows countries to go beyond what they have from their own services. And if you think about I don't know if we should say third world or global south or developing world or industrialized nations, but if you think about some countries, they have fewer resources and just, they're all looking for better forecasts. They want better observational monitoring. So if we can sort of patch together these resources globally and these national resources into one coherent picture, operating picture for everyone, that will be valuable. So it's a challenge, though. I mean, we've just spent the last year trying to define the standards. I've talked with many different groups, whether in South America or from Africa or Australia, New Zealand, who from the different services about what they have and how it could fit, and trying to figure out who's going to even host the global portal. Will it be ECMWF? Will it be NASA? So there's a lot underway in that arena. We took like 3 months and tried to make a little demo of how things would get merged. It's really not nice to look at. It was quick, but it was really for like the WMO leadership to get a sense of what the whole concept was. So we stood that up. It runs at Center for Environment in the UK. So the takeaways from all this is that there is this long-standing community of practice, and we work with that community of practice in land hydrology. All these terms, convergent co-development, R2O2R, fit for purpose, are all sort of describing this body of work that's going on all around us, really. And that there are a lot of very interested and motivated stakeholders who want to kind of take what we have here, if we can show it to them in a way that makes it seem relevant and connect it to what they do. There would be a lot of advantages for me. I tend to work with all kinds of models. It's like this horses for courses idea where, muddy track, you want a certain kind of horse, another dry track, a different kind of horse. One model does not work in all places, but for me, it'd be very convenient if we could find ways to use our own land modeling to connect into some of these applications. I think it would not only help us maybe start to get around this chain of models problem, because we could start to pull information directly out of coupled climate runs that was relevant not only for climate but also for hydrology, but we could also feed back information directly into the development process so that people understand the deficits and the strengths of the models that we're trying to run and whether they really do describe hydrology. So this is the last couple of slides, I guess, or a few slides. This really is the challenge I see for myself in the sort of next coming years, and it's basically to become more embedded in working on CTSM and CLM and trying to connect it over into this arena that I do a lot of work in and have a lot of expertise, which is more the stakeholder water resources. It's really interesting, though, I have to say, before I came and sat down in the TSS group, I had a sense of how land modeling groups work and think, but it was really not very informed. And one of the things that's become clear is that we think about things in a very different way. We're really thinking about the same water budget, as I'll show in the next slide. But here, like the general way of developing land models is to try to advance the fidelity of the model through improving things like the observational analyses, the parameterizations seem to become more real based on small-scale studies, and always, to some extent, increasing the complexity of the models we run. And basically, the model performance kind of emerges from all that, but it's not like the direct objective. It's really looking at a stand of trees and saying, you know what, we're really just not reflecting that canopy structure the way it looks in the real world. So let's like put in these details, whether it's a leaf angle or something else, and that will make it look more real. And then hopefully as a result of doing that, the performance of the model improves. Whereas in the applied hydrology world, it's kind of the reverse. All these things like the parameters we use, the physics and the structure of the model, and even the input quality emerges kind of as a result of trying to optimize the performance. If you try something, even if it might be realistic, but it makes the model worse, performance worse, you throw it out. So we're kind of working in different directions. And I think the philosophy here is, if we just keep going, we'll eventually represent everything with a big enough computer. And here it's sort of, we'll never afford to represent everything, but at least we have these optimization techniques and we can make the model perform well at whatever level of complexity. It is kind of really interesting, the contrast. Like the Earth system modeling community tends to look at this equation, like change in storage is the difference of precipitation minus evaporation or latent heat and minus runoff or discharge. And they also worry a lot about carbon. In fact, most of the discussion in TSS is probably about carbon. And then over here in this applied hydrology modeling community, we really worry about delta S, which is like snowpack and soil moisture and aquifers and precipitation and runoff, and don't really pay too much attention to evaporation. So it's kind of like we're working on the same equation, but we're not really interested in the same parts of it. And I mean, I cannot say how many hydrological modeling applications I've run where I did not ever look at evaporation or latent heat. And the issue is really if we try to solve all the terms, we have no degrees of freedom to make the ones that we care about look good. If I really worried about E in my ET, I'd have a harder time making runoff look good. And vice versa, if they really worried about runoff or anything in the subsurface, it would probably be really hard to make latent heat look good. And so it's just this, it's complementary vision, but in a way, we have to sort of figure out our way around working on them both together at the same time so that we improve everything. It makes our jobs harder. And so with this observation that runoff is really not a focus of attention in Earth system modeling, I had the pleasure of having Flavio Lehner come and do a postdoc with me down in RAL. I was doing all this applied stakeholder work. He kind of got exposed to the stakeholder water basin regional focus that we have. And we ended up doing a paper where we just said, okay, let's just show the world kind of what the climate runoff hydrology sensitivities in these coupled Earth system models is. And I pushed really hard to have some plots like this where we could just show as kind of brutally as possible, like how far off the coupled regional scale sensitivities to climate are, like the precipitation to runoff sensitivity in all these CMIP land schemes. If the observations are in black, the models are kind of all over the map in the Colorado Basin. And you can also see the sensitivities here, like, there's this one model 9, I can't even remember which one it is. It's just like so far off that you wonder like how the rest of the simulations are doing. And what we also showed further was if you did have good land sensitivities in these models, you would really constrain the uncertainty and improve and change the signal of what you project for their impact on hydrology. So for instance, here I guess like the unconstrained, default CMIP is this, but then if you actually use precipitation and temperature together, and then you apply the correct observed runoff sensitivity, the projection of a change in stream flow becomes far narrower, and then it shifts quite a bit, actually. So that, to me, this is the argument for putting this attention into the hydrology of these models. You know, ideally, we want them to work better, not just for climate, but so that we can actually say something about water security directly from the models. There's some good developments in this strategy that are going to help us a lot. One of the things is sort of data set that we, oh, that's good. Oh, here, I'll just take this call. If you can just, you just give me a minute. One of the things is a large sample data set. This is sort of an emerging direction in hydrology, and it's got a huge boost from some work that was done in RAL under projects. One project I co-led with Martin Clark and one that he led on complexity. In the first one, we set up this large sample set of basins to focus on, to look at predictability, hydrologic predictability across the country. And then a postdoc came from Switzerland, Nan Zador, and he added geophysical attributes. And so then we had these meteorological flow time series, geophysical attributes, many, many different kinds of catchments and different climates. And this actually kicked into high gear the entire sort of machine learning and hydrology effort that's been going on. I was just at EGU a few weeks ago, and the kind of lead who's been driving all the Google work in this area, they have a new Google Global Flood Hub, said he basically lived for 2 years kind of within this data set. And I've proposed to NCAR that we make, I mean, these data sets have had massive impact. They've been picked up by countries around the world. They're expanding it out. The Google lead, Freddie Kratzer, just released something called Caravan, which is, you know, thousands of basins around the world. And the idea is when we can look at hydrology from this broad perspective of many catchments, we can learn a lot about it that's going to help us develop our models and our techniques. And so this is one thing we've been using. I've started to have a postdoc who's working with me stand up kind of a CAMELS data set testbed for CTSM and CLM so that we can start to actually learn how to do hydrology in CLM from a large, very multi-basin perspective. So that's not just parameters, but also structures. Really understand, you know, why are we having so much trouble with these large-scale models, even when they're run at finer resolutions, in getting hydrology right. So, for instance, Go Chang Tang, who's here working with me, has put together a whole parameter estimation optimization workflow for CTSM, and we're starting to use it with the CAMELS as the reason, or as the testbed for this, but to start to optimize hydrology and flow coming out of CTSM. And it's not great, to be honest. Like, we can go through an optimization, and if this is a skill score that we want to be pushed all the way to 1, we can see that our optimization with parameters is able to move in that direction. That's good, but it's nowhere near close enough to use for applications now. There's still some things we need to learn about structure, parameterization choices. Even I've suspected for a while the depth of the model soil thickness is pretty much too deep for what we would tend to want to do in applied hydrology. So there are some things that we're using this to try to move forward with. Another big thing that's come along is this idea of being able to use statistical or machine learning emulators for models at the large scale. The reason for this is because our models don't run in 1/3 of a second like the conceptual models. They run very slowly because they're very complex. So the only way to really do kind of large-scale learning is to do something other than run your model. So we can train a statistical deep learning model on our model and then use that to estimate parameters and then connect it back with our model, update the deep learning model, keep going. So there's some papers that are starting to come out. This is one from colleague Xiaopeng Shen over at Penn State. I got this from Mark Bierkens, who just gave this as part of his Darcy Medal talk in EGU 2 weeks ago. And then here's another slide of sort of showing an example where they're starting to do this. This is with a land model called PCR Globe, and they've made a deep learning version of it. And you can kind of see it. This is a pretty fine spatial scale, but for things like surface runoff, subsurface runoff, the deep learning emulator is able to do a pretty good job of representing the full physics model. And so this kind of technique is going to be a central part of what we do moving forward to try to improve and calibrate and adjust the hydrology and fluxes out of our land models. And finally, this doesn't get us out of the woods. I'll just show a sort of cautionary figure. And this is from work by Yifan Cheng and Andy Newman over in Rao. This project started by Joe Hammond, working in the regional Arctic system model, where they've been trying to calibrate CTSM, the land model, for the coupled model simulations in the Arctic. And yes, as we find, you can improve stream flow. If this is the observed in red and the default coming out of the model would be in blue, we can adjust parameters and improve the agreement of the simulated flow to the observed flow. But what that does, as it brings down the discharge, again, we're back to this, do you worry about RO or do you worry about E? We sort of crank up the latent heat flux back in the atmosphere, which then induces a climate bias because it becomes too cloudy and too cold. And so we're into this issue where if we all work on our own component and then try to connect it, we basically solve our own problems but cause problems for everybody else. And it's not just a problem with Earth system modeling for climate. Groups that do numerical weather prediction, such as ECMWF or up in Environment Canada, they have the same issue where they can develop better land schemes, but when they couple them into the forecasting model, it makes the forecast worse. And so there have been some discussions around how you deal with this, and maybe, one idea is you couple things more, or couple these development activities more frequently. So you don't go for 2 years developing your model and then couple it all together and try to solve the problems. You basically have some process where every 6 months you kind of do a fully coupled run with what each new group, whether it's atmosphere or ocean or land, has done to their model. Because from our perspective, this is not our problem. This is the atmosphere's problem. Okay, we're going to give you a land model that works well. It has good climate sensitivities. You have to figure out why your atmospheric model with that land model is now too cloudy. Where maybe it's doing something wrong with the circulation, or I don't even know because I'm not an atmospheric scientist. But anyway, so this is kind of the issue that as a lab, we need to start to think about, how can we allow all the groups to move forward and get the best in their own areas and contribute it back. So that was, I think, my final slide, other than this. Well, it's actually, I lied, it's not. So basically the summary is we're working toward a better understanding of sort of how to converge these worlds of applied hydrology, Earth system science. And there are a lot of new data science techniques that are going to change our world and make this easier. We still have some problems that which I just mentioned, we're going to need to grapple with that are more structural for the lab. And I think we are still inadequately involving hydrologists. All my work is funded externally, essentially. I've never had really any funding from NCAR. So this is kind of ad hoc. So it's like I get projects, I try to steer them towards this, but it's not a way to really build a long-term research strategy. And so finally, just acknowledge some people. Is obviously an incomplete list. People have contributed ideas over time. I'm sure I left people out, so I didn't even actually want to write names there for the one person who says I should have been on that list. But there are a lot of different programs that have funded the work. And lastly, I was kind of asked to include a slide about leadership. So over the last 25 years, I've been involved in leading a lot of different things, some of which I mentioned, chairing the AMS hydrology or panel in CLIVAR, and one thing I'm kind of proud of is leading for 10 years or co-leading this international hydrologic ensemble prediction experiment, which brought me into contact with groups around the world and kind of built a community of practice around improving the modeling and science in all of our prediction practices. We wrote this really big handbook that came out a few years ago, which you can all have for $600 if you want. I think that's what they sell for. It's kind of overachieving because you get 2 doorstops instead of just one if you have 2 volumes. But so those are some of the outcomes of leading some of these initiatives and trying to get some of these ideas forward in the larger world. Lately, I think all my leadership has kind of been coming in this WMO activity, and that's kind of taking over all my time for other things. Anyway, thank you all for your attention. I don't see anyone sleeping, so that's a sign of success, I guess.
So thanks, Andy. We have time for questions. Maybe we'll start in the room and then let those of you online to get your questions in Slido.
Nice talk.
Thanks.
I enjoyed it. So just going back to Flavio's plot that you showed there, I mean, to me, this is the quintessential difficulty of climate modeling versus actionable science. So, you chose a very, very, very small region in a global model, and, you expose all the problems with that. I mean, you could go to a different region and different models would perform better compared to other models, and it seems an intractable problem. I mean, you could also go to one grid point and say, it looks terrible. Oh my gosh, this one grid point is terrible.
Yeah.
But there's a scale associated with the expectation of performance, and it probably isn't this scale. So I'm wondering, and it's not a criticism, I'm just trying to wrap around my head about the paradigm with which, we should develop climate models, knowing that this happens to be a very important region for us, at least in this room, et cetera, for the US. But there are probably terrible regions that don't matter to anyone that we do a really good job at. I don't know if that's true, but there's no reason to expect that that's not true.
Yeah.
So it just happens to be a region we all care about, and it's not so great.
Yeah.
I don't know what my question is, but that was the comment.
Okay. Monica? Yeah. I'm going to respond to him unless you have something to add to his question.
So I kind of do have something to add quickly. I think there's an additional problem that compounds kind of what Rich is bringing up. And I've actually used the paper by you and Flavio, and specifically model number 9, because we do a lot of the evaluations of models to determine if they're adequate for giving us information about locales based on whether they're consistent with observations. So do they have empirical adequacy? And the other plot of model number 9, which is the average runoff, it looks like it does really, really good for the upper Colorado basin.
Mm-hmm.
But then when you look at the sensitivity to precipitation, which I think is the plot that you had in your slide, it's just abysmal.
Yeah.
Right? And it's abysmal with respect to sensitivity to temperature too. And so it's a matter of looking good when you look at the average because of compensating errors. And so you have to look under the hood of these models too to determine whether the fields that they're using to calculate the properties that we're interested in are actually correct, and then also looking at representational adequacy. So I guess in a follow-up to Rich's question, how do you even get at some of these things that would allow us to determine if a model is actually adequate to be used at a local scale? Because empirical adequacy doesn't seem like it can be a sufficient condition for us to determine that the models can actually be used in these actionable contexts.
Yeah, I mean, to me, we need to start looking at the right things. And there is, one aspect to this that will be hard to solve, which is the fact that it is a small region. A lot of the models just have the wrong climatology of precipitation. They're 200% too much precipitation, which Colorado Basin would frankly love, but it's not the real world. Unfortunately, it's the model world. But that's fine. I mean, that's going to be something that has to get solved in larger issues with the ocean and atmosphere. But the land model sensitivity and converting that to runoff, that is something we can do something about. And so I think these models can all, even with their climatology biases, become useful or more usable if their change projection sensitivities are more correct, so that we don't have lines that are like this, but at least if they're, biased high or low, they're pointing us in the same direction. And so I think there are parts of that problem we can solve, and we should be able to solve for regions even the size of the Colorado Basin. Another problematic area of that is that climate modeling centers are the ones who are kind of more driving the push to use this runoff from these models directly. It's not coming from the hydrologist or the stakeholders, they would look at that and say, okay, that's garbage, like we're not going to use it. But I think the kind of groups that are going to California and saying, hey, look, I'm pulling runoff from my GCM and I'm talking about water security, and don't worry that the runoff all melts like a month and a half early from in the spring. I mean, these are the things that I think the climate community, part of the reason for this paper was actually to talk back to the climate community and say, hey, some of this stuff at the regional level is not ready for prime time in water security assessment. So that's an issue. But yeah, the adequacy problem, I think we need to start looking at the ability to project change, not just the ability to simulate our current climatologies, which is far and away what most of us do. And I think things like ideas like emergent constraints are useful. That's one possible strategy toward weighting some models higher than others, but it's not enough. It's just a start. Rich? Or no, sorry, go ahead.
Well, along the same lines, even if you just choose one model, say the CSM, and look at the large ensemble, isn't there a huge amount of variability between those ensemble members when you get down to the regional scale of a river basin?
Definitely, and this is another problem. I think I had a paper on sort of back in 2012 looking at the Colorado Basin saying, basically, oh my gosh, if you run MPI 4 times, you either have 30% more water or 30% less water, and that's not just in a 10-year period, that's over a 30-year period. So yeah, we've come to appreciate the problem of internal variability, and I think this is all the more reason why we need to be able to go directly from these models to our analyses, because the fact that we now have to look at large ensembles makes everything else harder. So if we don't have to downscale anything or run it through an offline model, then maybe we can look at a large ensemble because it'll be more efficient. We'll go directly to the source and then interpret it. So yeah, I think internal variability is a big issue, unforced climate variability.
Thanks. I was just wondering about with the applied philosophy of just getting your parameters right to get the right answer and not worrying about evaporation. How much attention is being paid to the fact that we're in this changing climate, and one set of parameters that maybe worked in the 80s, maybe do they work now? Are people assessing that?
Yeah, I think I'm a little bit representative of a lot of hydrologists, and since we don't need to worry about carbon or ET, we tend to not, and then it's helpful. But I do think there is a lot of concern, particularly as we see these dramatic changes in our landscapes and in our runoff response, that we need to have things like dynamic vegetation in our models that can change and evolve. And actually, that's another reason for why I'm very interested in sort of introducing models like CTSM to stakeholders and saying, look, even though you don't need this for streamflow, this might be the model you want to use to go forward with, because it's going to simulate some things that, in SUMA, we don't represent that, and it's obviously limited. But I will say, oftentimes with this, if you have a model that has some ability to reflect some of those changes, even like effects of soil moisture on ET through canopy restriction. I mean, to some extent, that's not the full, enchilada in terms of canopy response to carbon dioxide, but it gets you somewhere. And so you can see over a 30-year period, your model actually does present a pretty good covariance between climate and hydrology, and it looks good in the 80s, and it also looks good in like 2010s. So I think models are, at least for now, a little more flexible than we sometimes give them credit for. And you tune the parameters and they do well. You can do cross-validation. But I do think we're coming to an era where we need this even greater physical realism, like to bring that into the applied context.
Thanks, Andy. I thought what you said towards the beginning about shifting your mindset from modeling grid cells to modeling watersheds was really interesting. So
Yeah.
I was curious if you could talk a little bit more about how you've done that, and does it make it easier to connect with stakeholders? But then how do you sort of go back to the modeling community that's very, traditionally very sort of grid cell
Grid
based?
based. It definitely, I think, helps with stakeholders. It's always been attention to show these gridded models, particularly at like 16th or 8th degree, to a bunch of, water resources people or hydrology people. I do feel like people are not that comfortable with it. I mean, early on in my career, there was tin-based model triangles that came out of MIT, and that really never got going. I mean, it's still out there. There are people who developed it as grad students are now professors, but really that was even more a stretch, and maybe it was very efficient, but I do think those kind of details matter to the stakeholders. And now with the new geospatial data sets, we can show them simulations that have these rivers that they recognize, and they're exactly aligned with where the river really is. And I think those all add to the credibility, whether the model's good or bad. And I actually think what's happening is the Earth system modeling community is coming to support those kind of representations, because I think they also see some value in it. Even though I have to tell you, it will take you 10 times longer to write a plot script that is on watersheds than on a grid, or to visualize it. Like, you can't just NC view your outputs, So it comes at a cost, but I think the realism is worth it.
Question from Peter, and then maybe if there's time as a moderator, I'll ask one.
Thanks, Betty. Andy, I love this idea that we've started off with these very discrete sort of research activities like system modeling versus catchment sort of level. And a lot of your work seems to be trying to bridge and bring together so that we can inform across these efforts. Do you have any sort of guidance how NCAR can align itself to better inform between our research efforts so that we can get a maybe more consistent sort of understanding of the Earth system and the climate system for actionable science?
Yeah, I mean, I think part of it is just getting a handle on what people are doing in the organization. Because even I work in that applied science area, and I know there are all these other activities going on that are, potentially relevant that I don't even know exist. And I think if that's true for me, I think that's true for leadership as well. And so some idea of how you could bring more synergy across from the applied efforts with the more base development efforts. I mean, obviously funding is an issue, and SAM and all the rest, like, we don't tend to base fund people doing applied work as much as developmental work. That's, I think we've known about that issue for a while. But I also think valuing, this question comes up a lot, like, you show something and it's on a small watershed, and the immediate thought in people's mind is, well, how's that relevant to like larger Earth system modeling? That's just one place. But there are these techniques, like through this large sample watershed, this idea that we should be able to learn from things that don't work or do work in small local areas, because where else are we going to learn from it, and bring them back into the larger domain. Ideally, the result of all this work on parameters and model development is it builds a better land model for global simulation, not that it builds a better land model only for Colorado Basin or something. So it's making that connection. I think there's lots of ways to make it, but we just have to value it, I think.
Okay, so it's noon.
Oh, excellent.
So let's thank Andy.
Thank you.